So then enter my prodigal fellow, Mike McDermott. So Mike McDermott, a good Irishman, had been in my lab and had eschewed any involvement in periodic fevers while he was in my lab. He was interested in the genetics of rheumatoid arthritis. But when he took a real job over in London, he decided that he would track down that original Irish-Scottish family from Great Britain. There we are with the Spanish Armada. In any case, you see? So in any case, so Mike McDermott, there he is, had gone out and tracked down this original Irish-Scottish family with so-called Hibernian fever, and had done some linkage studies because it was a fairly big family. This was back in 1998 after we had found the gene for FMF. And it turns out that the gene mapped to the short arm of chromosome 12. And remember that the gene for FMF is on the short arm of chromosome 16, so that pretty much told us that the theory of the Spanish Armada, although an interesting one, probably wasn't right. So in any case, Mike came back over to my lab to do a sabbatical, sort of the prodigal son. And so he came back, and it was a fairly large region on chromosome 12 where the gene might reside, with a lot of immunologically interesting genes in that region. And so we applied the embarrassment test. The embarrassment test is basically, well, what gene would it turn out that if you spent 5 years looking for it, which one would be the most embarrassing, if it turned out to be that one? So it turns out that in this region, TNF-RSF1A resides, which is the gene that encodes the P55-TNF receptor. And since TNF, tumor necrosis factor, is a major mediator of fever and inflammation, we thought, well, that would be really embarrassing if it turned out to be that. So in any case, this was in October of 1998. And on Thanksgiving Day of 1998, Mike and Ivona Aksentievich in my lab came in to check their sequencing electropherograms and found 6 mutations in 7 different families with dominantly inherited recurrent fever in the P55-TNF receptor. So anyway, it was really a great Thanksgiving Day. So in any case, a lot to be thankful for. This is just what the protein looks like. This is what the P55-TNF receptor protein looks like. There's actually also a P75 that's encoded on chromosome 1. So it has 4 extracellular cysteine-rich domains, a transmembrane domain, and then a death domain, so it makes a cousin of pyrin, because the death domain is similar in structure to a pyrin domain. Anyway, these patients turned out to have, at least a lot of them, turned out to have mutations at cysteines that are involved in disulfide bonding of the extracellular domain. And the disulfide bonds basically maintain the 3-dimensional structure of this in a way that allows it to bind to TNF. So we thought that that was at least somewhat of an explanation why things might go wrong in these patients. And so we actually then, following April, published a paper with Cell describing these mutations in patients with dominantly inherited periodic fever syndrome. The cover of Cell, actually, this is taken from the autopsy of the husband of the woman who called. So this is amyloid deposits in the kidney of the husband of that lady and the father of the patient that you didn't really get a chance to hear from. And then this is the pedigree of it. So this disease, which we renamed because it turned out that in the Irish family, the so-called Irish family, the mutations came from the Scottish side of the family, so we didn't want to call it Hibernian fever after all. So we decided that rather than having any sort of ethnic implications, that it probably would be better just to call it something that would be relevant to the cause of the disease and easy to remember. So we came up with TRAPS, TNF receptor-associated periodic syndrome. And so this disease, TRAPS, is caused by dominantly inherited mutations in the P55-TNF receptor. There's really no ethnic predilection to it. There's a defect in activation-induced receptor shedding, in patients who have this, which we thought at least initially might explain the inflammatory phenotype. And it was at the point where we found these mutations that we came up with this idea of autoinflammatory diseases, because we had then seen two different genes, the one encoding pyrin in FMF, and now this one, that caused inflammatory conditions, recurrent inflammatory conditions, without high-titer autoantibodies or antigen-specific T cells. And of course, it later turned out that these turned out to be disorders of the innate immune system. So in any case, just for those of you who are interested, here are some images from various TRAPS patients. I've already shown you this one, the adhesions in the peritoneal cavity of a young girl with repeated abdominal attacks. Here's pleural thickening in a middle-aged man with TRAPS. Here's the rash of TRAPS, which is quite interesting. It's a migratory rash. Erythematous, if you do an MRI, it turns out that there's inflammation going down into the fascia in these patients, and it migrates down the extremity. Here is periorbital edema, which you would have heard about on the video, and then here is amyloidosis in the kidney of our patients. So in any case, since the time that we have found these mutations, my good friend and colleague, Richard Siegel, has done a number of cell biology experiments looking at the effects of these mutations. And it turns out that they have broader effects than just the problem with the shedding of the receptor from the cell surface. So that, for example, if you transfect wild-type receptor into the cell line, it turns out to localize the bulging, whereas mutant receptor gets hung up in the endoplasmic reticulum. So this is sort of a constipated picture for these leukocytes. And you can see that if you take cells from patients, this is not just in cell lines, patients that have TRAPS-associated mutations have, in fact, marked retention of TNF receptor intracellularly. In any case, that leads to ticklishness of the leukocytes. And so if you stimulate the cells from TRAPS patients with various things like LPS and then look for TNF production, at least at very low doses of LPS, you see that the patients, shown in the filled bars, have much higher responses than controls. And so essentially the threshold has been changed in these patients. And looking at this from the standpoint of various signaling pathways, it turns out that phosphorylation of gene kinase is increased in cells of patients who have TRAPS. So in any case, what we think, at least another part of the story in terms of how this happens, ordinarily TNF leads to the aggregation of TNF receptors on the cell surface and the engagement of a signaling complex, which then leads to the release of various pro-inflammatory cytokines. With the misfolding of the receptor, it causes intracellular aggregation of TNF receptors, which basically brings together death domains in a way that engages the signaling complex and basically leaves things in an on position. So in any case, now I'd like to change gears again and talk about yet another set of recurrent fever syndromes. And these are ones that are particular favorites of mine, although they're all really nice. And these are disorders that are sometimes called CAPS, for the cryopyrin-associated periodic syndrome. These are disorders, three different diseases that are all caused by mutations in one gene. And it turns out that that gene encodes a protein that's in the pyrin family. So that's really fun and interesting. So what all three of these diseases have in common is an urticarial skin rash, shown here. This happens to be a patient with Buffalo-Wells syndrome. It's urticarial because, in point of fact, they don't have true urticaria where you'd see mast cells and high levels of dystrophin. They have actually granulocytes that are in these lesions, so they're not true urticaria. The three diseases are FCAS, familial cold urticaria, or familial cold autoinflammatory syndrome, which is a really interesting, dominantly inherited disease in which patients get cold-induced fever and an urticarial skin rash. Second one is Buffalo-Wells syndrome, in which patients don't necessarily have cold induction of their symptoms, but they get fevers, rash, arthritis, sensory neural hearing loss, and amyloidosis. And then the most severe, which I mentioned to you before, NOMID, neonatal onset multisystem inflammatory disease, which in Europe is called SINCA syndrome, chronic infantile neurologic